Fermat's little theorem. In this session, we will be discussing what is Fermat's little theorem or simply Fermat's theorem and certain applications of Fermat's little theorem. Before going to the theorem, let us have certain observations on numbers. You consider a prime number, say 7, and another integer a equal to 12, taken with the property that p does not divide a. Here you can see that the residues of the numbers like 1 into 12, 2 into 12, 3 into 12, 4 into 12, 5 into 12 and 6 into 12 modulo 7 are the numbers 1, 2, 3, 4, 5, 6 in some order, because 1 into 12 is congruent to 5 mod 7, 2 into 12 is congruent to 3 mod 7, 3 into 12 is congruent to 1 mod 7, 4 into 12 is congruent to 6 mod 7, 5 into 12 is congruent to 4 mod 7 and 6 into 12 is congruent to 2 mod 7. So the residues of 1 into 12, 2 into 12 etc. up to 6 into 12 modulo 7 are the same integers 1, 2, 3, 4, 5, 6 but in some order. Now we are going to generalize this result. There is a lemma which states that if P is any prime and A is any integer such that P does not divide A, then the least residues of the integers A, 2A, 3A, etc. P minus 1 into A modulo P are a permutation of the integers 1, 2, 3, etc. P minus 1. Permutation of 1, 2, 3, etc. P minus 1 means it's an arrangement. Say an arrangement of these integers in some order. That's all. Now let us try to prove this. Here we want to show if P is any prime and A is any integer such that P does not divide A, then the multiples of A by 1, 2, 3, etc. P minus 1, that is 1A, 2A, 3, etc. P minus 1A are such that the residues of these integers modulo P are 1, 2, 3, etc. P minus 1 in some order. We prove this First, we will show any I, for any I in between 1 and p minus 1, IA is not congruent to 0 mod p. That is, IA is not a multiple of p. This is because, suppose IA is congruent to 0 mod p. Here I is such that 1 less than or equal to I less than or equal to p minus 1. For any I, IA is not congruent to 0 mod p. Suppose IA is congruent to 0 mod p, then p divides IA. Then p divides IA. But p is a prime number such that p does not divide a. That is, pa equal to 1. And therefore this implies p divides I, which is impossible since I is such that 1 less than or equal to I less than or equal to p minus 1. I is a number in between 1 and p minus 1. So p cannot divide I. And therefore IA is not congruent to 0 mod p for any I 1 less than or equal to I less than or equal to p minus 1. Next we will show if IA is congruent to JA modulus P for any I 1 less than or equal to I comma j less than or equal to p, we will show I is equal to j. If IA is congruent to JA, that is any multiple of A, some multiple is another multiple. IA is congruent to J mod P, where IJ are such that 1 less than or equal to I comma j less than or equal to P, then I is equal to J. How to prove this? Here PA is 1. We have taken P and A are such that PA is equal to 1. And therefore IA congruent to J mod P implies I is congruent to J mod P. J mod P. I congruent to J mod P means since I and J are least residues modulo P, this implies actually I is equal to J. I and J are least residues modulo P, and here I is congruent to J mod P, that is P divides I minus J, that means I minus J should be 0, that is I is equal to J. So we got the result that any multiples, two multiples of A if you take, IA and JA if you take, they are congruent modulo P if and only if I equal to J, same multiple. And therefore no two least residues of A, 2A, 3A, etc. P minus 1 into A are congruent modulo P. That means the residues of A, 2A, 3A, etc. P minus 1A modulo P are the distinct integers 1, 2, 3, etc. P minus 1 in some order. Hence the result. Now we go to the Fermat's little theorem. The theorem says that if P is any prime number and A is any integer, such that P does not divide A, then A raised to P minus 1 is congruent to 1 mod P. A raised to P minus 1 is congruent to 1 mod P. So let us try to prove this. If P is any prime number and A is any integer such that P does not divide A, then A raised to P minus 1 is congruent to 1 mod P. By previous result we saw that the residues of A, 2A, 3A, etc. P minus 1 into A modulo P are the integers 1, 2, 3, etc. P minus 1 in some order. Some order. Residues. Residues of A, 2A, 3, etc. P minus 1 into A modulo P are 1, 2, 3, etc. P minus 1 in some order. That means A into 2A into 3A into etc. P minus 1 into A is congruent 1 into 2 into 3 into etc. P minus 1 modulo P, because A, 2A, 3A, etc. P minus 1 A in some order are congruent to 1, 2, 3, etc. P minus 1 modulo P, and therefore their product is congruent to 1 into 2 into 3 into etc. P minus 1 modulo P. A into 2A, 3 etc. P minus 1 into A is A raised to P minus 1. There are P minus 1 A's and 1 into 2 into 3 into etc. P minus 1 is congruent to 1 into 2 into 3 into etc. P minus 1 modulo P. That is A raised to P minus 1. This is P minus 1 factorial is congruent to P minus 1 factorial mod P. Again we have the result that if AC congruent to BC mod M and C is such that Cm equal to 1, that is C and M are relatively prime, then A is congruent to B mod M. Here P minus 1 factorial and P are such that they are relatively prime. That is GCD of P minus 1 factorial and P is 1. Because up P minus 1 factorial it is only up to P minus 1, then it is clearly relatively prime with the P. Therefore, cancelling this P minus 1 factorial, we get A raised to P minus 1 is congruent to 1 mod P. Thus, the result, Fermat's little theorem. Actually, the theorem was proposed by Fermat, and only after a century the result was proved by Euler. Now, let us illustrate this Fermat's little theorem by taking the examples P equal to 7 and A is equal to 12. Here P does not divide A. 7 does not divide 12. So the least residues modulo of 1 into 12, 2 into 12, 3 into 12, 4 into 12, 5 into 12 and 6 into 12 are modulo 7 are 1, 2, 3, 4, 5, 6 in some order. And therefore 1 into 12 into 2 into 12 into 3 into 12, 4 into 12, 5 into 12, 6 into 12, the product is congruent to 1 into 2 into 3 into 4 into 5 into 6 into 6 mod 7. That is 1 into 2 into 3 into 4 into 5 into 6, which is actually 6 factorial into 12 raised to 6. There are 6 12s here. Is congruent to 1, 2, 3, 4, 5, 6 product mod 7. That is 6 factorial into 12 raised to 6 is congruent to 6 factorial mod 7. Here 6 factorial and 7 are relatively prime, and therefore 12 raised to 6 is congruent to 1 mod 7, which is the Fermat's little theorem. P is 7, A is 12, P does not divide A, and therefore A raised to P minus 1, 12 raised to P 7 minus 1, 6 is congruent to 1 mod P, that is 7. Now there are several applications for Fermat's little theorem. One of the use is to find the remainder when a number of the form A raised to n divided by a number P, where P is such that P does not divide A. Such cases we can use Fermat's little theorem for finding the remainder. So let us take an example of that type. Find the remainder when 29 raised to 24 raised to 1947 is divided by 70. We know 24 is congruent to 7 mod 17. We want to find the remainder when 24 raised to 1947 is divided by 70. This type of problem we did it already, but here we are using Fermat's little theorem for finding the remainder. 24 is congruent to 7 mod 7. 17. 7 mod 17. Therefore, 24 raised to 1947 is congruent to 7 raised to 1947 mod 17. You take this 1. Here, by using Fermat's little theorem, here taking A is equal to 7 P is equal to 17. Clearly 17 does not divide 7, and therefore 7 raised to A raised to P minus 1, 17 minus 1 is congruent to 1 mod 17. That is 7 raised to 16 is congruent to 1 mod 17. Now this 1947, by using division algorithm, you can write as 16 into 121 plus 11 on division by 16. This 16. 1947 you can write as 16 into 121 plus 11. Therefore, using 1, 24 raised to 1947 is congruent to 7 raised to 1947, which is congruent to 7 raised to 1947 is, you can write as 16 into 121 plus 11 mod 17. Again it is congruent to 7 raised to this, you can write as 17 raised to 16 raised to 121 into 7 raised to 11 mod 17. Now 17 raised to 16 is congruent to 1 mod 7 by 2. So this is congruent to 1 into 7 raised to 11 into mod 17 by using 2. Take these 3. Again, we know 7 square is congruent to minus 2 mod 17. So 7 square is 49 plus 2 becomes 51, it is a multiple of 17. Therefore 7 square raised to 5 is congruent to minus 2 raised to 5 mod 17. That is 7 raised to 10 is congruent to minus 2 raised to 5 is actually minus 32. Minus 32 mod 17 and minus 32 is congruent to 2 mod 17 because minus 34 is a multiple of 17. So minus 32 mod 7 is congruent to 2 mod 17. Hence 7 raised to 11 you can write as 7 raised to 10 into 7, which is congruent to 2 into 7 mod 17, because 7 raised to 10 is congruent to 2 mod 17 by this. So 7 raised to 11 is equal to 7 raised to 10 into 7, therefore it is congruent to 2 into 7 mod 17. That is congruent to 14 mod 17. You take this 5, then using 5 from 3, hence from 3 we get 24 raised to 1947 is congruent to 1 into 7 raised to 11 mod 17, which is congruent to 14 mod 17. Hence the remainder when 24 raised to 1947 is divided by 70 is 40. Hence the remainder is equal to 40. Now another theorem which is deducted from Fermat's little theorem is that if P is any prime number, let P be a prime and A any integer such that P does not divide A, then A raised to P minus 2 is an inverse of A modulo P. Inverse of A modulo P. If P is any prime number and A is any integer such that P does not divide A, then A raised to P minus 2 is an inverse of A modulo P. Let us prove this. We know A is the inverse of B if AB is congruent to 1 mod P. If A and B are such that AB congruent to 1 mod P, then we say B is the inverse of A and similarly A is the inverse of B modulo P. So here we want to prove A raised to P minus 2 is an inverse of A. That means A into A raised to P minus 2 congruent to 1 mod P. So this is to be proved, and that is very clear from the Fermat's little theorem. Here P is a number, prime number such that P does not divide A, and therefore by Fermat's theorem A raised to P minus 1 is congruent to 1 mod P. But A raised to P minus 1 you can write as A into A raised to P minus 2 is congruent to 1 mod P. Hence by the definition of inverse, it says that A raised to P minus 2 is the inverse of A. Inverse of A modulo P. Hence the result. Now another result is that it's a theorem, again another application of Fermat's theorem. Let P be a prime number and A is any integer such that P does not divide A, then the linear congruence AX congruent to B mod P has a solution which is given by X is equal to A raised to P minus 2 into B modulo P. So this is one of the applications of Fermat's little theorem. By using this result, we can find the solution to a linear congruence in the form AX congruent to B mod P. That is, to solve the linear congruence AX congruent to B mod P, just use the result. X is that the solution is the residue modulo of a raised to p minus 2b modulo p. Now we have to prove this. Given p does not divide a, and therefore by Fermat's theorem we have a raised to p minus 1 is congruent to 1 mod p. This shows that a raised to p minus 2 is the inverse of a modulo p. Earlier we found, and therefore multiplying the given linear congruence ax congruent to b mod p by a raised to p minus 2, we have a raised to p minus 2 into ax is congruent to a raised to p minus 2 into b mod p. There is a raised to p minus 1, p minus 1 into x is congruent to a raised to p minus 2b mod p, but a raised to p minus 1 is congruent to 1 mod p, and therefore x is congruent to a raised to p minus 2 into b mod p. So we have the result that a solution to the linear congruence ax congruent to b mod p is given by a raised to p minus 2 b mod p. Let us take a problem of finding the solution to a linear congruence using Fermat's theorem. Suppose we have the linear congruence 12x congruent to 6 mod 7. We have to find a solution to the linear congruence 12x congruent to 6 mod 7. Here a is 12, p is 7, and clearly p does not divide a, and therefore the solution to the linear congruence is x congruent to a raised to p minus 2 b modulo p, a raised to p minus 2 modulo p. Here p is 7, a is 12, so this is 12 raised to p minus 2, 5, 7 minus 2, 5 modulo 7. Into 6, a raised to p minus 2 into b modulo p. So 12 raised to x is congruent to 12 raised to 5 into 6 modulo 7. Now 12 we know, 12 raised to 5 is congruent to 3 mod 7. This we can verify, and therefore this is congruent to 3 into 6 into mod 7, which is congruent to 4 mod 7. Thus 12x congruent to 6 mod 7 has a solution 4 mod 7. Residue of 4 mod 7. Now let us take another example of solving linear congruence by using Fermat's little theorem. Solve the congruence 24x congruent to 11 mod 70. The given congruence is written as 7x congruent to 11 mod 70. Since 24x is 17x plus 7x. So 24x congruent to 11 mod 17 can be written as 7x congruent to 11 mod 17. Here 7 and 17 are such that 17 does not divide 7, and therefore by using the Fermat's theorem it has a solution x congruent to 7 raised to 15 into 11 modulo 70. We have the result that Ax congruent to B mod M, B mod P has solution A raised to P minus 2 into B mod P. That is the residue of A raised to P minus 2 B modulo P is the solution to Ax congruent to B mod P. Here P is 17. So A is 7 here. So 7 raised to 15, that is 17 minus 2. 7 raised to 15 into 11 mod 17. Now we have to find the least residue of 7 raised to 15 into 11 modulo 7. Now to find the residue of 7 raised to 15 into 11 modulo 17. We know 7 square is congruent to minus 2 mod 17. Therefore, 7 raised to 4 is congruent to 4 mod 17, minus 2 square mod 17. 7 raised to 8 is congruent to again 4 square 16, and 16 mod 17 you can write as minus mod 17. So 7 square is congruent to minus 2 mod 17, and 7 raised to 4 is congruent to 4 mod 17, and 7 raised to 8 is congruent to minus 1 mod 17. Therefore, 7 raised to 15 you can write as 7 raised to 8 into 7 raised to 4 into 7 square into 7. This is 7 raised to 50, which is congruent to 7 square is congruent to minus 2 mod 17. 7 raised to 8, 7 raised to 4 are like this. So 7 raised to 8 is congruent to minus 1. So minus 1 into 7 raised to 4 is into 4 mod 17. 7 square is minus 2 into 7 mod 17. And this is congruent to, just multiply, you will get 56 mod 17. Which is congruent to 4 mod 17. You know. പതിനേഴും 34 7 40 51 54 5. Actually it is 5 mod 17. It is 5 because 54 you can write as 51 plus 5. So 5 mod 17. And therefore x is congruent to 7 raised to 15 into 11 mod 17 by this one. So it is congruent to 7 raised to 15 is congruent to 5 mod 17. So 5 into 11 mod 17, that is 55 mod 17, and this is congruent to 4 mod 17. 51 plus 4. 51 is a multiple of 17. So x is congruent to 4 mod 17. So these examples show that Fermat's theorem can be used to solve linear congruence in the form Ax congruent to B mod P, where A and P are such that P does not divide A. If it is asked independently, the previous method is better, but if you are asked to prove using Fermat's theorem solve, you have to go this way only. Now we prove another result. It's a theorem. If P is a prime number and A is any positive integer, then A raised to P is congruent to A mod P. That is another result that we get using Fermat's little theorem. For Fermat's theorem, actually, P and A are such that P does not divide A should be there. But here, P is any prime number and A is any integer such that then A raised to P is congruent to A modulo P. The proof is done by taking two cases. Case 1, let P does not divide A. In that case, by using Fermat's theorem, we have A raised to P minus 1 is congruent to A mod P. A raised to P minus 1 is congruent to 1 mod P. Now multiplying by A, we get A into A raised to P minus 1 is congruent to 1 into A mod P. That is, A raised to P is congruent to A mod P. We have the result. Now let us take the case 2 where P divides A. Let P divide A. That is, A is a multiple of P. A congruent to 0 mod P. We take this 1. Therefore, A raised to P is congruent to, again, 0 raised to P mod P. That is, A raised to P is congruent to 0 mod P. Number 2. Also, by 1, since A is congruent to 0 mod P, and its congruence is a symmetric property, from 1 we have 0 is congruent to A mod P. 3. Then using 2 and 3 and applying the transitive property, A raised to P is congruent to 0 mod P and 0 is congruent to A mod P, and therefore by using transitive property, A raised to P is congruent to A mod P. So in any case, whether P divides A or P does not divide A, we have A raised to P is congruent to A mod P. Take the case, an example, P equals 7, A is equal to 12. We know P does not divide A here. In this case, we know by using Fermat's theorem, twelve raised to 6 is congruent to 1 mod 7. Multiplying by 12 on both sides, we get 12 raised to 7 is congruent to 12 mod 7. A raised to P congruent to A mod P. 12 raised to 7 is congruent to 12 mod 7. Now, suppose A is equal to some number like 28 and P equal to 7. Here, P divides A. In this case, we are expecting (28 raised to 7) is congruent to 28 mod 7. We know 28 is congruent to 0 mod 7. So 28 raised to 7 is congruent to 0 mod 7 is congruent to 28 mod 7. Mod 7. So in any case, whether P divides A, P does not divide A, we have A raised to P is congruent to A modulo P. Now there is another theorem which is again application of Fermat's little theorem. The theorem is this: if P1 and P2, P3, etc., Pk be any distinct primes such that A is any integer and L equal to the LCM of P1 minus 1, P2 minus 1, P3 minus 1, etc., Pk minus 1, then A raised to L plus 1 is congruent to A mod P1, P2, etc., Pk, the product P1 into P2 into etc., Pk. Proof is simple. We have by Fermat's theorem A raised to Pi minus 1 is congruent to 1 mod Pi for all I equal to 1 to etc. k. Since L is the GCD of Pi minus 1 for I equal to 1 to k, every Pi minus 1 divides L. Therefore, L is a multiple of Pi minus 1 and cell divided by Pi minus 1 is an integer. Since L is equal to LCM of Pi minus 1, Pi minus 2, etc., Pi minus k, L is a multiple of these. Therefore, L by Pi minus 1 is always an integer for all I. And therefore, A raised to Pi minus 1 raised to L by Pi minus 1 is congruent to 1 raised to L by Pi minus 1 mod Pi. That is, A raised to L is congruent to 1 mod Pi. Therefore, A raised to L plus 1 is congruent to A mod Pi. That is the result. As an illustration, okay, this is A raised to L plus 1 is congruent to A mod Pi. We haven't proved the given result. Here A raised to L plus 1 is congruent to A mod Pi for all I is equal to 1 to etc. k. That means A raised to L plus 1 is congruent to A mod P1, A raised to L plus 1 is congruent to A mod P2, etc. like that. Therefore, A raised to L plus 1 is congruent to A mod LCM of P1, P2, etc. Pk. That is congruent to A mod. Since P1, P2, etc. Pk are distinct primes, LCM of P1, P2, etc. Pk is nothing but the product P1, P2, etc. Pk. And hence A raised to L plus 1 is congruent to A mod P1, P2, etc. Pk. That is the final result. So, as a verifying, this result, let us take P1 equal to 3, P2 equal to 7, P3 equal to 11. Here L is actually the LCM of P1 minus 1, that is 3 minus 1, P2 minus 1, 7 minus 1, 11 minus 1, which is equal to 2, 6, 10. LCM of 2, 6, 10 is actually 30. And therefore, by this theorem, we are expecting A raised to 30 plus 1, A raised to 31 is congruent to A mod P1 into P2 etc. Pk, that is 3 into 7 into 11. That is A raised to 31 is congruent to A mod 231. 3 into 7 into 11 is 231. So A raised to 31 is congruent to A mod 231 for any integer A, for any positive integer A. Now there is a corollary to this theorem. That is, if P1, P2, etc. Pk are distinct primes, then A is any integer and L is the LCM of P1, Pi minus 1, then A raised to L plus 1 is congruent to A mod P1, P2, etc. Pk. The corollary is this. Let A be any integer and P any prime greater than 3. Then A raised to P is congruent to A mod 6P. A mod 6P. Now we are applying this result. A raised to L plus 1 is congruent to A mod P1, P2, Pk, where L is actually the GCD LCM of P1 minus 1, P2 minus 1, etc. Pk minus 1. For that we need some P1, P2, etc. here. We want actually the product is 6P, so this is nothing but 1 into 2 into 3 into P. So 2 into 3 into P. So let us take, to prove this, let P1 equal to 2, P2 equal to 3 and P3 equal to P, and apply the previous theorem. Here L is equal to P1 minus 1, LCM of P1 minus 1, P2 minus 1, P3 minus 1, which is LCM of 2 minus 1, that is 1, 2 and P minus 1. Since P is a prime greater than 2, P is an odd number, so P minus 1 is an even number. Therefore, the LCM of 1 to P minus 1 is nothing but P minus 1. And therefore, we have the result A raised to L plus 1 is congruent to A mod P1, P2, etc. Pk. Here A raised to P minus 1 plus 1 is congruent to A mod the product 2 into 3 into P. That is, A raised to P is congruent to A mod 6P. Hence the result.